My name is Pradeep Kumar, the Oregon Chapter Chair, and the Vice Chair, Rath Vanatambi, will be moderating the session. I'll hand over to Rath.
All right, thank you, Pradeep. So I'm Rath Vanatambi. I'm very happy to introduce our speaker today, Dr. Xingqin Lin. He's a senior standards engineer at Nvidia, leading 3GPP standards research on 5G, 6G, and AI. Before joining Nvidia, he was with Ericsson, led 5G, 6G research and standards, and contributed to 5G NR, NB-IoT, and LTE standards. He's a co-author of the book, Wireless Communications and Networking for Unmanned Aerial Vehicles, and lead editor for the book 5G and Beyond, Fundamentals and Standards. He has over 80 papers and 200 patent applications with over 7,000 Google citations. He has received several prestigious awards, including IEEE Communication Society Fred W. Ellersick Prize in 2021 and the Vehicular Technology Society Early Career Award in 2021 and the WCNC Best Paper Award in 2020 and Communication Society Best Young Professional Award in Industry 2020. He was included in the list of AI 2000 most influential scholars in the field of Internet of Things in 2021 and 2022, and the list of world's top 2% of scientists in 2020 and 2021. He served as an editor in many journals. Him and me work on the Internet of Things magazine. In addition to that, he has been with IEEE Communication Letters, Communication Magazine, Network, and also he has been a guest editor for several special issues in Communication Magazine, feature topic, aerial communications, and the wireless communication special issue on AI-powered telco network automation, 5G evolution, and 6G, and also JSEC, 3GPP technologies, 5G advanced and beyond. He's a fellow of IET and a senior member of IEEE. He holds a PhD degree in the electrical and computer engineering from the University of Austin. So now, without any further ado, let's welcome our speaker to talk about that exciting topic, AI for 5G advance towards 6G. Welcome, Xingqin.
Yeah. Thank you. Thank you, Rod, for that extremely generous introduction. And also thank you for inviting me to give this webinar. Today, I will share our Nvidia vision about embracing artificial intelligence in 5G evolution towards 6G. Before that, I would like to share a 3-minute video. I hope my Zoom doesn't crash. If my Zoom crash, I will rejoin. So please bear with me. Let me start with sharing the video.
I am an explorer, traveling across the Atlantic to unlock its mysteries, and back in time to understand the origins of the universe. I am a visionary, bringing sharper focus to researchers. And brilliant clarity to surgeons. I am a healer, making treatments as unique as every patient, and giving new life the chance to thrive. I am a guardian, looking out for dangers around us. And in the depths below. I am a helper, enabling healthier, more sustainable crops. Bringing them to market faster and preparing them for the table. I am a creator, building virtual worlds to help robots learn faster and make our connections stronger. I am even an avatar, and you can ask me any question.
Who made this song?
Ava used artificial intelligence to write this song, and it was recorded by the London Symphony Orchestra. I am AI, brought to life by Nvidia, deep learning, and brilliant minds everywhere.
Okay, I hope you enjoy this short video. So let's get to the main discussion of today's presentation, which is closely related to artificial intelligence. Okay, let's get started. I think many people know Nvidia for our presence in the video gaming space. Our professional line of GPU is used in workstation for applications in fields such as architecture, engineering and construction, media and entertainment, automotive, scientific research, and manufacturing design. Some people of you may be aware that Nvidia also provides an application programming interface called CUDA that allows the creation of parallel programs that utilize GPU. So GPU together with CUDA are deployed in supercomputing sites around the globe. In more recent years, we have become recognized for our presence as the DNA of data center compute infrastructure and also for leadership in artificial intelligence, in robotics, autonomous vehicles, computer graphics, and even gaming with our deep learning super sampling that improves graphic performance significantly. However, not as many people are aware of our work in wireless communication. In recent years, we have been doing research and development on GPU solution for 5G and 6G together with artificial intelligence. So today, we will talk more about our work in this line of direction. So here's the agenda of this webinar. We'll start with a short introduction to artificial intelligence and also 5G. After that, we'll look at how Nvidia AI on 5G solution can help solve some of the most challenging problems in 5G. Then we'll discuss the latest status of 3GPP work about embracing artificial intelligence in 5G evolution, both from 5G architecture perspective and air interface perspective. In the end, we'll look at the 3GPP roadmap from 5G to 6G and then conclude this webinar. As mentioned earlier, please feel free to stop me whenever you have questions. I very much enjoy interactive discussion. At Nvidia, we believe every industry will be transformed and reshaped in the next decade. So the immense forces of artificial intelligence, digital transformation, and 5G connectivity are combining and will create unprecedented opportunities in business and society. As conventional computing and Moore's law started to hit limits, accelerated compute for both application and infrastructure are very important. Accelerated compute started to become an essential element to achieve the required functionality and performance. We used to think of CPU serve as the basic unit of computing, but to meet the demands of today's machine learning and AI workloads, we must optimize the entire data center from end to end. So the new unit of computing has now transitioned to be the data center itself, dimensioning the right balance of three essential technologies: CPU, GPU, and DPU to enable scale-out and scale-up computing. Artificial intelligence automates intelligence. We just entered the second wave of artificial intelligence. Recently, I think many of you have noticed the huge interest sparked by the ChatGPT. The first wave was reinventing computing. So we, together with the early adopters and internet companies, has been driving that first wave for more than 10 years. Now the second wave is happening in the enterprise and also at the industrial edge. So we need to turn artificial intelligence from computer science running in the cloud into smart AI products at the edge and also in billions of connected devices and computers. We call this AI on 5G at Nvidia. Billions of things can be located throughout the network, and data center will not be connected at all points in the network. A data center where you need it and when you need it. So where does 5G come into all of this? We believe a ubiquitous 5G network will connect these data centers and intelligent things at the data rate, latency, cost, and power required by the application. So the use of artificial intelligence, 5G, and edge computing to enable Industry 4.0 is a key focus for us at Nvidia. And we'll hear more about this line of work later in this presentation. Of course, you are probably already familiar with the CPU, flexible and responsive. For many years, CPU were the only programmable element in most computers. More recently, the GPU has taken a very important role. Originally used to deliver real-time, very rich graphics. Now their parallel processing capabilities make them ideal for accelerated computing. Thanks to these capabilities, now GPU are essential to artificial intelligence, deep learning, and big data analytics application. Accelerated computing requires more than just a powerful chip. We believe incredible speedups needed full stack invention, from the chip and the system to the algorithm and the application they run. 5G brings new values. 5G redefines the present market and opens new marketplaces. 5G network capabilities go far beyond previous generation of mobile communication. It enables a wide range of applications and use cases. For example, in retail, smart cities, healthcare, media and entertainment, transport, and industrial application, as shown in this slide. So these applications and use cases can leverage a tailored mix of the 5G capability to develop differentiated service experience compared to 4G LTE. For example, 4K video, a smartphone uses large data volume and benefits from capabilities such as extreme data rates, where AR, VR, and mobile gaming will also require additional capabilities like low latency and high reliability for good user experience. So in summary, 5G provides the underlying connectivity for billions of devices, extending the reach of artificial intelligence and applications to all connected objects at the edge, enabling new use cases and new markets. We are just embarking on the evolution journey of 5G Advanced. Last year, 3GPP started Release 18, which was the beginning of 5G Advanced. So we're still in the era of 5G, and we'll still be in 5G Advanced for some time as new 3GPP releases are formulated and 5G network continue to be rolled out. However, I think many of you have noticed that 6G research is already well underway. So in order to have 6G supporting a wide range of new and evolving services, we believe 6G network capabilities need to be enhanced and extended in many dimensions compared to 5G networks. 6G will play order of magnitude KPI improvement requirements over those of 5G, just like we did over each generation. We may expect 10x user data rate, 5 to 10x improvements in spectral efficiency, and an order of magnitude of even more reduction in latency and an order of magnitude increase in connectivity density. Besides this traditional KPI, we believe it's also important to focus on new capabilities related to, for example, service availability, security, and the capability of local compute integration. So while we are likely to see a move to terahertz frequency in 6G, and also the network becomes a holistic communication and sensor network, many other fundamental capabilities will underpin 6G. For example, softwareization of the system, heavy use of software-defined radios, virtualization, and of course, AI everywhere. So we are now transitioning into the era of big data meets wireless. The massive parallel computing can support AI and also signal processing. So GPU hardware will play an important role in the continued 5G rollout, 6G research, and eventually 6G deployment. Okay, mobile networks such as 5G system we just described, we realize they are becoming increasingly complex for supporting different deployment scenarios and different applications. So the evolution of this 5G system for improving performance and also addressing new use cases make all these systems become very sophisticated. So we realize there are many technical challenges in such complicated system, from system modeling to algorithm development to network configuration, and also these systems generate humongous data. The use of rapidly advanced AI techniques, such as machine learning and data analytics, is critical to managing this complexity, identifying patterns in the data, optimizing the network design, enhancing system performance, and also reducing operating costs. So to accelerate wireless innovation, we need a powerful computing platform to enable researchers and engineers to combine simulation, data analytics, and artificial intelligence. So at Nvidia, we're developing end-to-end reference design to make our products better and also for others to use in their own research and product development. So this slide shows our reference design. It's a platform for researchers and product developers working in the area of software-defined radio, 5G, cloud, and in particular, the combination of 5G machine learning and cloud. As wireless networks are becoming increasingly complex, the importance of performing accurate simulation for such complex systems cannot be emphasized enough. So the software framework at the center of our most powerful simulation technology is called Omniverse. We have used this in our drive and robotics program called ISIC for bringing digital twin to reality and also for tasks such as reinforcement learning for robotics. We won't get into the details of Omniverse in our presentation today, but we believe it has the potential to be a game changer in many facets of wireless research, development, and deployment in the future. Omniverse can enable real-time physically accurate simulation, virtual reality, collaboration, and realizing digital twin. So there's a lot more interesting research to be done in this area. The notion of a digital twin has been taking off in many industries, such as smart manufacturing, construction, bioengineering, and automotive. However, I would say digital twin remain relatively new for us in telecom, especially for 5G and 6G. We expect digital twin to be a powerful concept for 5G networks and beyond. As the 5G rollout continues, digital twin have the potential to access network performance, predict the impact of environmental and system changes, and optimize network configuration, operation, and decision-making processes. So taking advantage of this Omniverse platform, the wireless industry is already making progress towards building digital twin network. For example, you may find from the internet news about Ericsson build a city-scale 5G digital twin in Omniverse. This slide shows another example. Heavy.ai has recently launched telco digital twin application built in Omniverse as well. Okay, so next I would like to discuss a bit more about AI on 5G platform. So this platform has been deployed. In general, Nvidia platforms and solutions have been deployed in many different cloud applications. But now we realize increasingly more customers are looking into AI at the edge or device-based AI to enhance their products and services, and also to transform their workflows. So Nvidia is extending our AI know-how into the enterprise compute sector. So AI on 5G is a unified platform that brings together development in artificial intelligence and 5G to accelerate the digital transformation. We are now in a new era of industrialization driven by AI and digital automation. So the data center, as mentioned earlier, is the new unit of compute. So now the data center will be where you need it and when you need it, at the edge or in the device. So this data center will be connected through a high-performance 5G network, a network that is driven by artificial intelligence to be energy and spectrally efficient and also self-organizing. So these technologies come together on our AI on 5G platform. This will drive innovation and kickstart the next industrial revolution. So this slide shows the end-to-end block diagram of the AI on 5G platform. Starting from the left, we have the many different types of devices that can be connected to the platform. Going to the right a bit, we have the 5G radio. So here, the all-round radio unit implements the digital front-end signal processing. It also implements the low 5 functions, including OFDM modulation, anti-modulation, and also some aspects of beamforming. Continuing to the right, we have the hardware. Here we have compute resources, the GPU for signal processing and machine learning, the network interface card supporting the front haul interface, and also CPU hosts for layer 2 and the above protocols. The rightmost figure shows the software stack. At the bottom, we have the Nvidia management orchestration solution, such as free command. Moving up the stack brings us to area 5G. Here we have the baseband functionality, purely software defined and implemented using GPU and combined with CUDA. The next layer highlights our enterprise solutions. And on top of that, we have NVIDIA Unified Compute Framework. At the top layer, we have many NVIDIA AI application framework that can run together with the communication connectivity service. Here we see some more details of the hardware. So the hardware is based on NVIDIA Converging accelerator, which combines the computational power of the GPU with the network acceleration and security benefits of CPU, all in a single high-performance package. Here we see some more details about the signal processing performed on the GPU using so-called CUFI. In this case, we only show the PDSCH and the PUCH, but all the NR control channels, for example, the physical downlink control channel, PDCCH, or the uplink physical control channel, PUCCH, are all realized on the GPU. They're just not shown in this figure. The baseband signal processing pipeline implemented in CUDA is run entirely on the GPU. The radio link control, or the MAC layer, and also scheduler are hosted on the CPU. So we realized
one question,
yes,
can you comment on what is 5G aerial?
Oh yes, 5G area is our software framework. We call that NVIDIA Aerial. So Aerial is SDK. We implement the baseband functionality in software. We call that solution Aerial. And then when we say 5G, AI on 5G, that means we combine not just the communication part, but also the AI application into the same platform. That's what we call AI on 5G. Does that clarify?
Yes, thanks.
Yeah. Okay, So we have noticed that the mobile industry, in fact, has been accelerating the use of the state-of-AI techniques in wireless communication. But to a large extent, the current use of AI techniques primarily relies on proprietary implementation and solutions. Global standardization has enabled mobile technologies to scale and flourish over the past decades. We all witness that. We anticipate that the standardization will again play a key role in accelerating AI application to mobile networks. So from that perspective, 3GPP has been studying AI-enabled radio access network in release 17, including the principles, functional framework, use cases, and solutions. So next, let's take a look at this 3GPP study. As we discussed earlier, 5G networks are expected to meet the challenges of consistent optimization of a large number of KPI, including latency, reliability, connection density, user experience. At the same time, we have to address the complex system design and optimization issues introduced by advanced 5G NR features, such as multi-connectivity, multi-radio dual connectivity, beamforming, and network slicing. Mobile operators see this traditional human-machine interaction very slow, error-prone, expensive, and cumbersome to handle these challenges. So AI, including machine learning algorithms, provide a powerful tool to help operators to improve the network management and the user experience by analyzing the data collected and also processing the data autonomously so that we can generate further insights. So these considerations motivated 3GPP to investigate standardization aspects for AI-enabled next-gen radio access network. Although most of the AI algorithms can be up to implementation, there are certain aspects deserve studies in 3GPP. So especially these include the signaling support for the training and the execution of the AI models. The data required by the AI models, these data may come from reported by the UE or collected from different parts of the network, and also the outputs generated by the models to be delivered to other parts of the network. So before the introduction of standardization support for artificial intelligence, it will be beneficial and desirable to get some common understanding within the 3GPP community on the concept of artificial intelligence and the AI framework commonly used in the current or future networks. We all know that 3GPP is a very big community. Achieving globally aligned understanding is always challenging. For this study, it was considered that potential use cases and examples should be discussed to identify the AI enabling features. So therefore, this study aimed to study the functional framework for RAN intelligence enabled by further enhancement of data collection through selected use cases and identify the potential standardization impact on current 5G architecture and interfaces. So during the study, 3GPP adopted a set of key principles to focus on AI application with potential standardization impact. So one key principle here is that the detailed AI model, for example, whether to use a decision tree or a neural network, is not within the scope of this study. Instead, this study focuses on identifying the essential information needed or produced by the AI models for each use case. We'll look at the use case later. So compared to classical algorithm development, a very distinct nature of AI models is their learning nature. So the study investigated the standard impacts of both model training and inference, but the details of the training, such as the number of training iterations and how the training should prioritize certain data samples, these are not within the scope of this study. So this study focused on the AI functionality and corresponding input outputs. The input output and the location of the model training and the model inference function were studied case by case. So this study should identify a general framework and workflow for AI optimization, but the framework and workflow are not supposed to be limiting thinking outside of the box is needed if a use case requires so. Last but not the least, 3GPP acknowledge that user data privacy and anonymization should be respected during AI/ML operation. Okay, we mentioned the functional framework for AI for next generation radio access network. So this slide shows the functional framework identified in the 3GPP study. So starting from the left, we have data collection. It's a function that provides input data to model training and model inference. Examples of input data may include measurements from the devices or different network entities, feedback and output from AI models. Going to the right, we have model training and model inference functions. So model training is a function that performs the training, validation, and testing, which may generate performance metrics as part of the testing procedure. Model inference is a function that provides inference output, for example, predictions or decisions. It can also provide model performance feedback to model training function when needed. On the rightmost, we have the so-called actor function. So this is a function that receives the output from the model inference function and triggers or performs corresponding actions. So in addition to studying high-level principles, functional framework we just discussed, this study also investigated potential use cases and identified potential solutions for the use cases. So the outcome of this study was documented in Technical Report 37-817. Now 3GPP continued the normative specification work in release 18, which is ongoing. So the objective of this work item is to specify data collection enhancement and signaling support within existing 5G interfaces and architecture. The selected use cases include network energy saving, load balancing, and mobility optimization. We know that now network energy saving is very important on the agenda of many operators. So the rapid growth of 5G deployment brings the issue of high energy consumption, carbon emission, and high OPEX. The optimal energy saving decision depends on many factors, including, for example, the load situation at different nodes and different radio access network node capabilities, KPI requirements, number of active devices, cell utilization, user mobility, among others. So here, the thinking is that we can use AI model to predict the energy efficiency and also load state of the next period, then which can be used to make better decisions on cell activation or deactivation for energy saving. Load balancing is another important use case. So the rapid traffic growth and also the many frequency bands utilized in commercial 5G network now make it very challenging to steer the traffic in the balanced distribution. So load balancing can be done by optimizing handover parameters and handover actions. So here, based on collections of measurements and feedback from devices and other network nodes, historical data, so we can use AI-based model to predict load situation so that we can improve load balancing performance to provide better user experience and improve the system capacity. Mobility management is critical for service continuity by minimizing, for example, call drops, radio link failures, unnecessary handovers, and ping-pong effects. So for application characterized with very stringent QoS requirements, such as reliability latency, the quality of experience is sensitive to the handover performance. So from that perspective, AI model can be used to enhance the mobility performance. They can reduce the probability of unintended handover events. They can be used to predict UE location and use the prediction for traffic steering, for example. Your question?
Yeah, I have a question. So can you comment on, what is the level of, gain, so advantage found since, it looks like already a work item in 3GPP?
Yeah, that's a good question. The work I'm discussing now is more from architecture perspective. It's conducted by Luan 3. So Luan 3, they usually don't do detailed performance evaluation. But the other study, which is about the work on air interface, so that as part of that study item ongoing in release 18, people at different companies try to look at the performance gains. So we can talk more about that later. Yeah.
Okay, thank you. There is another question from somebody, Yashin.
Yes.
You can,
yes.
ask. Yeah.
Yeah, Shin. Actually, my curiosity is more towards the practicality of this, how to really execute into the current CSP's environment, where you have the multiple OEMs coming into picture, Shin. So how 3GPP is really looking that kind of a challenge in the real world to really get this use cases implemented. See, I hope you got my challenge here, or I shall elaborate my question more.
So yeah, you refer to the multi-vendor.
Yes, I refer to the multi-vendor scenarios. You know, all the CSPs are having the mixed bag of the multi-vendors, right? Where
Yes.
the interoperability is really kind of a challenge to be really met first before these use cases can get that foundation layer to be get executed itself, right? Because if that foundation layer is not there, these use cases are just running over the thing as a hype only.
Yeah, I think that's a very good comment. So if we look at the current, the mainstream RAN, right? It's monolithic to a large extent. So they come from a single network vendor. And then I think now we all realize Open RAN is a very popular trend in the industry. Now, if we have different vendors addressing different use cases or even the same use case, how do we really harmonize and make sure interoperable? That's a challenge. I think O-RAN is addressing in that direction. Later, we will talk about a different interoperability issue. We will look at air interface. For example, we'll talk more about this later, about CSI compression. So there's a different interoperability issue between network vendors and UE vendors. How do we match encoder and decoder from network vendor, UE vendor? So all these are challenges the industry need to resolve. So these are open. I will not say they are well solved now. I think you rightly acknowledge, pointed out the difficulty here.
Okay, thank you.
Yeah. Any other questions or comments? All right, if not, we can continue. I think we already mentioned about, okay, there's another study ongoing in 3GPP, which is really focused on the UU interface. So this is the key focus for 3GPP standardization over the years. So the thinking is that to reap the full benefits from AI techniques in 5G and beyond, we must optimize the integration of AI into the system design and realization, including the air interface, not just from the network side itself. And then I think people have been talking about native AI 6G for many years, and people believe that is the trend. And we can, from timeline perspective, we can think that 6G standardization may likely start in 3GPP around 2025. So we will have a window of opportunity until 2025 to achieve a globally aligned way forward for integrating AI into the design of air interface. So therefore, despite the fact that the 5G air interface, so-called new radio, has largely been frozen, there is really an urgency to begin to get going to investigate AI-enabled air interface for 5G evolution in 3GPP release 18, which started last year. So in this study, 3GPP explores the benefits of augmenting the air interface with features that may enable improved support of AI-based algorithms to enhance performance, reduce complexity and overhead. So here, enhanced performance depends on the use cases under consideration. They could be, for example, improved throughput, robustness, accuracy, or reliability. So here, by looking into a few very carefully selected use cases, assessing their performance in comparison with traditional methods and the associated specification impact, this study will lay the foundation for future air interface use cases, leveraging AI techniques. So the objective here is that we need to look into sufficient use cases to enable the identification of a common AI framework including functional requirements of the AI architecture, so that we can leverage for AI native design on the way to 6G. And in this study, we identify where AI could improve the performance of AI interface function. I think, Rod, you ask a very relevant question. How much gain do we really get out of these AI algorithms and models by replacing traditional functionality? So that is an ongoing exercise in VGPP. And this study will also identify what is required in order to have an adequate AI model characterization and description. This is very important because, as mentioned earlier, VGPP is a very large community. It's important to establish a common language in VGPP to build consensus. This study also carries out evaluation to quantify the gains of AI-based techniques for the use cases under consideration. So as part of the evaluation study, certainly there will be results submitted by different companies, right? So the goal here is to have a better understanding of the achievable gains and also the associated complexity requirements. So these investigations, functional framework, improvement areas, model characterization, and evaluation will pave the way to assess the specification impact. This is very critical for improving the overall understanding of what will be required to enable AI techniques for the AI interface. So I want to provide, also show you some detail, some more detailed discussion carried out in the VGPP. One aspect is about the network UE collaboration levels. So in this slide, we show a few examples on the collaboration levels. So starting from the left, we have the baseline. Here, there's no collaboration between the Genobi and UE. So you can think of the current network. There may be some network vendors or UE vendors already leverage AI techniques, but they are purely based on proprietary implementation and solutions. So in this case, we do not change the AI interface specifically for the AI models running either at the network side or at the UE side. Then in the middle, we have so-called signaling-based collaboration without model transfer. So compared to the first case, the difference is that in VGPP release 19, for example, we may modify AI interface and introduce new signaling to facilitate the efficient AI ML-based features, such as introducing new measurements and reporting to facilitate the AI ML operation. On the right, we have a so-called signaling-based collaboration with model transfer. So here, model transfer means we deliver an AI ML model over the AI interface. So it can be transfer of the parameters of an already known model structure or even a new model with a new structure and parameters. So these are initial categories defined by VGPP. They may be further refined depending on the progress in VGPP. So as mentioned earlier, this study investigates VGPP framework for AI-powered AI interface. There are 3 use cases selected in this study. One is CSI feedback enhancements, which we'll talk more about this later. The other is beam management enhancements, which may look into, for example, beam prediction in time and spatial domain. Last but not the least, the third use case is positioning accuracy enhancements. So here, different companies see quite significant accuracy improvement by using AI ML algorithm to do positioning compared to traditional geometry-based positioning. VGPP delivers specification for mobile networks. So of course, the study on AI for AI interface will assess the potential specification impact, especially for the agreed use cases, and also to establish a common framework. So from physical layer perspective, we need to consider aspects related to, for example, AI model lifecycle management, data construction for training, validation, and test for the selected use cases. We need to look into use case and collaboration level specific specification impact, such as new signaling, ways for training and validation, assistant information, measurement, and feedback, just to name a few. From protocol perspective, we need to consider aspects related to, for example, capability indication, configuration and control procedure, and also management of data and AI model. Also, we need to look into collaboration level specific impact according to each use case on the protocol stack. Interoperability and testability, we briefly talked about this earlier. These are very critical for real world deployment. So here we need to study requirements and testing framework to validate AI-based performance enhancements. So we need to ensure that UE and Genobi with AI solutions meet or exceed the existing minimum performance requirements defined already, for example, by 3GPP Rainfall. So next, I would like to, yes, please.
Can I interrupt? And
Yeah.
So in the previous slide, you mentioned for the CSI, not CSI, the positioning accuracy, there is a huge gain.
Yes.
How about the other two, CSI feedback and the beam management?
Yeah, so for beam management, the gain is also quite significant. So from beam management, two sub-use cases were examined by different companies. One is beam prediction in spatial domain, and the other is beam prediction in time domain. So both, I think the majority of the companies show quite considerable gains. And then for the CSI enhancement, there are also two sub-use cases. One is so-called CSI compression, which we'll talk more about later. So there, I would say the results are a bit more modest, I would say. There's a variety of gains shown by different companies from a few percent to 100%, right? So it's very difficult to say definitely what would be the gain, because it depends on so many assumptions and scenarios. And also from CSI perspective, there's also CSI prediction. So I think people observe quite noticeable gains from that perspective, because we know that channel aging is an important issue, especially when it comes to high mobility and MU-MIMO scenario. You really need accurate CSI. If you don't have the CSI prediction capability, then you have to use aged CSI, which affect your performance. So I would say, in general, there's a wide range of spectrum in terms of gains. So what is important from 3GPP perspective is to find promising use cases and to introduce specification impact. But also more importantly, on the path to 6G, we establish a common framework so that we don't need to start from scratch at 6G. Yeah.
So if I understand right, CSI prediction, pretty good. CSI compression, moderate. Is that right?
That would be my assessment, but that's not formal 3GPP
yeah.
conclusion at this stage.
Okay, all right.
Yes.
Thank you. Got it.
Yeah.
There's another question.
Yes,
Brad, I have a question too after.
Okay.
Should I go ahead and ask? So you mentioned you may need to transfer the model between the network and the UE. Is there a use case for that?
Yes, I'm going to talk about this use case in particular. This is a very
and just a quick question also. Yeah, what kind of capabilities are required on the UE? So does it need to have some fast acceleration capabilities, or
yeah, I think that's a very good question related to UE capability. Certainly, I think this, in order to be capable of utilizing a model delivered from the other side, there may be some new requirements from UE capability perspective. But all these are pending, ongoing discussion, nothing settled on yet.
Thank you.
Yeah.
There's one more question. Harry, you can unmute and ask your question.
Okay, thank you. Yes, I do have a couple of questions. One question is about coexistence. Are you envisioning having one AI algorithm implementation that is standardized, or are you allowing for different vendors to have their own different implementations that sort of coexist and work together? I'm thinking particularly with these UE devices as they age and become legacy devices and new AI gets rolled out in the network. Is there any thought around how to maintain backward compatibility and coexistence with different AI algorithms? And the other question was about coexistence with other standards such as Wi-Fi using AI techniques.
I think that's a good question. In general, the current trend in the standardization body like 3GPP, the thinking is that the detailed AI model and structure should not be standardized, because that's not good from innovation perspective, right? For example, we always advance the technology to introduce new AI models and algorithms. So from standardization perspective, it's unlikely that there will be a model or algorithm standardized in the specification. So what standardization will do is to facilitate what is needed in order to support AI model and algorithms. For example, what data will be needed to support the operation, and what signaling will be needed to support the operation. Does that answer your question?
Yes, yes. It sounds like though there's just going to be some kind of interoperability testing of different vendor implementations to make sure they don't do unexpected things.
Exactly. That's the one part of the scope within the reinforced scope, right? They need to ensure interoperability and testability so that minimum performance requirements can be met. In the current implementation, for example, using classical algorithm, right? We can set the minimum requirements, but it's challenging also for 3GPP Reinforce to figure out new ways to make sure this data-driven AI ML model also meet certain minimum performance requirements. So that's an open area. Okay. And then on your second question related to, for example, working with how to interoperate with other standard body, I would say at this stage, 3GPP has not considered that part yet. Now we focus more on, for example, this study, right? It's more within the 3GPP UU interface between Genobi and UE. Right? If there are no other questions, we can continue. I think it's good to discuss a more specific use case so that you get more concrete insights. So here, I want to motivate that use case using massive MIMO. We know that massive MIMO has been quite successful in 5G commercial deployment. It has been deployed in many different countries. And during the field deployment, I think people observe there's also room for improvement. So given the importance of massive MIMO in mobile networks today, and it will continue to be important on the path to 6G, it's motivated to investigate how AI can be used to improve massive MIMO performance. So here I want to use the CSI acquisition, for example. So there are certain drawbacks of existing CSI acquisition methods. For example, one, we know that in TDD deployment, we can use uplink reference signal to acquire CSI, but they have coverage issue and it's mainly limited to TDD networks. And we also know that UE usually have more antennas for receiving than for transmitting, right? So UE may need to switch antennas to transmit uplink reference signal for the uplink-based CSI acquisition. However, in reality, there is a lack of wide UE support for antenna switching. And also, the existing CSI feedback for FDD is mainly use codebook-based scheme. So here, it is codebook-based. The resolution may not be high enough to support a multi-user MIMO, and also the acquired CSI may be sensitive to UE speed. That's why CSI feedback is a use case selected in this AI ML for augmenting air interface study. So I think I will skip this slide. This slide basically shows the existing CSI feedback in 5G NR specification. On a high level, there are two types of codebook, type 1 codebook and type 2 codebook. And they are codebook based. So people realize that the overhead may be reduced and the resolution may be increased by using AI ML algorithms. So that's the main idea. So here, the idea is that to use AI techniques such as autoencoders for CSI compression reporting. So the basic principle of autoencoder is to take an input, perform some nonlinear compression by encoder to a lower dimensional latent representation, and then decompress the representation by decoder to a defined target. So here, the the principle of the autoencoder is illustrated in the bottom figure in the context of CSI compression. So here, the UE estimated channel state is taken as the input to the encoder, and then the output of the UE's encoder is quantized and transmitted over the air interface to the base station. And then the base station can use a matching decoder to reconstruct the channel state. So you can see that the autoencoder model is divided between the UE and the base station in this use case. So there's some internode dependency for model training management among others. So that really are touched upon on the interoperability issue we just talked about. So if we want to use this autoencoder-based solution for CSI compression reporting, then we need a neural network in the UE to interact with a compatible neural network at the base station side. From base station perspective, the decoder needs to be trained to match different UE vendors implementation, but it's quite challenging to have a separate model at the base station for each UE vendor's implementation. And I think there's some discussion earlier about legacy UE and new UE, right? If you have new device type, do we really need a new decoder? That's a question under discussion. And also from the UE side, it's not possible to have a separate encoder at the UE side for each base station vendor's implementation. So you can see these multi-vendor interoperability is really a challenge. For such two-sided model, you have encoder at the UE side and decoder at the base station side. So this is a very challenging problem under discussion in 3GPP. And then in this slide, we show a few training options for the autoencoder-based CSI feedback under discussion in 3GPP. So starting from the left, we have the joint training at a single entity in a single training session. So the entity can be at the network side or the UE side. If the training is done at the network side, the network need to transfer the encoder model to the UE. So I think we had some discussion earlier about model transfer, right? Is this needed? I think this is one example where model transfer is needed. When the model is transferred trained by the network, then the model may need to transfer to the UE or vice versa. And then in the middle, we have joint training at two sides in a single training session. So in this case, the encoder model and decoder model are trained at UE and base station, respectively. But the models are trained in the same loop for forward propagation and backward propagation by exchanging forward activation and backward gradient between UE and base station. On the right, we have so-called separate training at two sides in different training sessions. So there's no collaboration during training, but we need some coordination outside the training process to ensure that the UE side and network side model are compatible. So in this case, we can have separate training starting with UE side or separate training starting with the network side. So take the separate training starting with the UE side, for example. In the first step, the CSI encoder model is trained by a UE side entity. And then the UE side entity can share a training data set consisting, for example, encoder output and target CSI with the base station entity. After that, the base station entity can train its decoder model based on the data set. As you could imagine, there are pros and cons for each option. It can take another hour to discuss the pros and cons for each option. I think these ongoing discussion in 3GPP, it'll be interesting to see eventually which option will be selected by 3GPP. Okay, I think I have a few final slides to wrap up the discussion. So first, let's recap the 3GPP timeline from 5G to 6G. We know that 3GPP completed the first release of the 5G specification as part of its release 15 back to June 2018. So that laid the foundation for commercial 5G deployments worldwide. Since then, 3GPP has been working on evolving 5G technology in release 16, release 17 to improve performance and also address new use cases. I think at the end of 2021, 3GPP approved the work package for its release 18, and the work started in 2022. So that work marks the start of 5G advanced evolution. 6G is still in research phase, as we mentioned earlier. The focus is on the technology components and systemization. And we can expect that 6G commercialization may happen around 2030. So working back from 2030, we feel there's some urgency to get going. So the standardization in 3GPP is likely to start around 2025. So we need to join forces to create and sustain the momentum. Okay, here are some concluding remarks. We talk about AI. We believe AI is driving technology evolution or revolution, and embracing AI in 5G evolution towards 6G is a very important direction in wireless communication. As more and more AI ML items are being conducted by 3GPP, we can expect that the AI adoption in wireless communication will be accelerated beyond proprietary solutions in years to come. So we will have the opportunity to design the 6G system based on a data-driven architecture that will utilize large amounts of data to support AI across cloud, core network, radio access network, and device. So the future of 6G is exciting. The journey towards 6G should be taken in collaboration with academic community and also industry partners to have a globally aligned way forward. So we look forward to co-innovating for the future with you. That concludes my presentation. I hope this webinar gives you some perspective on AI for 5G evolution towards 6G. Thank you for your attention. I welcome your questions or comments, if any.
Thank you, Xingqin. Now we have time for questions. Please unmute and ask your questions if you have any.
So just small one for this further reading 3 references actually, which are mentioned below, especially the second one, 6G digital twin networks from theory to practice. How I can get access, or how the forum can get access of this paper?
If you just Google the title, you should be able to find it. It's on archive.
Oh, wonderful. Perfect. Yes. It's open access.
Yes, okay. all 3 should be can be found by Google search.
Perfect. Then. Thank you.
I have a question on the performance of the auto encoder. So like what kind of gains are you seeing? Like, are you, I think Rath asked this question, but are you being, can you compress the feedback channel more? Like there's some significant amount of compression, or is it giving you better performance in terms of data rates? Like what are the metrics and, what's being seen?
Yeah. There are different metrics, right? If we can purely look at the compression ratio, just as you just mentioned, right? We can also look at how, let's say, this AIM model provides better compression ratio. Then how does this reduced compression translate into system performance gain, right? If you have reduced compression, but still at the same level of accuracy, then you reduce your uplink overhead. And hopefully, then you can use the resource for data communication. So both the model-specific KPI and the system performance KPI are being looked at by 3GPP community.
And one more question was like the privacy aspect. Like if you're sending your model, this compressed model back to the network, is there any privacy concerns there or not?
Exactly. I think that's a very valid point. For the type 1 training I mentioned earlier, training done at a single entity and then share the model with the other entity, right? There's certainly a proprietary implementation concern, right? I think maybe either Genobi or UE does not want to disclose their implementation to the other side. So that's why some of the options we talked about earlier may less likely to happen compared to some others. If you look at training option 2 and 3, they don't require this model transfer, right? At each side design their own encoder and decoder respectively, and then you have some coordination in terms of training. So from that perspective, privacy or proprietary concern may be better preserved for training option 2 and 3.
And just from the methodology perspective, how
Yeah.
are you verifying the performance? Like, are you making sure that you're training and testing in different scenarios? Like, how do you prove robustness of these algorithms?
Yeah, I think that's an excellent question. I don't have the answer. I hope VGPP going forward will have the answer soon. It's certainly a very difficult question, right? Because these AI ML model, everything, they are data driven.
Exactly.
Yes,
It's
yeah.
function of the data you got. Okay, yeah.
That's certainly a very key issue VGPP need to resolve.
We'll have to define the methodology, right, for testing.
Yeah. They need to also, likely, just like you said, they need to come up with a new methodology of testing.
Maybe I have a question. So, in your point of view, what in 6G, what kind of AI techniques do you think will get in?
It's from Nvidia perspective, we would like to see AI everywhere. So that's that's our vision. We want to see AI everywhere, from physical layer to network layer, and from end to end, from radio access network to core network, everywhere. So we would like to see AI penetrate as much as possible to telecommunications.
So maybe the question, Xingqin, by the way, good presentation, thank you, is yeah, I mean, AI everywhere is a good objective, but again, we are balancing performance gain versus complexity and power cost as well, both in the device side as well as on the network side. So it's a balancing act. So you said RAN 4 is looking into some of the study items that doing, say, the autoencoder, building on what Shilpa asked, or this model exchange. I mean, the benefit that I'm going to get on the AI interface or the network performance side versus how much extra power and processing or complexity that I'm going to introduce. That study, what's the timeline for those kind of studies? I mean, is the 3GPP is doing all this new model and trying to generate the what is the benefit out of it, but do you have a timeline in mind?
Yes, we do. So when it comes to the timeline of this study, which is a very high profile important study within 3GPP, this study item is supposed to be completed by end of this year. So hopefully by then we will see a technical report published by 3GPP documenting the findings. But that's not the end of the story, right? And then in release 19, I expect 3GPP will continue maybe with a small work item, trying to introduce some more promising. We talk about a lot of AI use cases today, right? Maybe only a few of them will get into release 19, but as time goes, like release 20, 21, there will be more and more AI components in 3GPP system. And we only talk about radio access network part. In fact, there are also a lot of AI studies and ongoing in the SA part, which focus on the core network side. Yes.
So the end of December is that's the example. One of the example you gave is this on a massive MIMO side of it. Is that the report you're talking about? That end of December we'll get?
Yes, that will be part of the report. The CSI compression using autoencoder. Yeah, this is a very challenging use case. Or for the other use cases like positioning and beam management, right? Maybe you can deal with a single-sided model. You don't really need to deal with this two-sided model. So that's why this use case is of particular interest. I brought up here.
Very good. Thank you.
Hi, I have a question.
Yes,
first
please.
of all, just want to thank you for giving this presentation. It's great. Learn a lot. So I know another thing that 6G is looking into is non-terrestrial network, especially with, for example, satellite systems. Is there any sort of collaboration between the studying of enabling sort of non-terrestrial network applications and what AI could do to help with that use case?
Yeah, I think I like this question due to my personal experience. I work a lot on non-terrestrial networks. If you search some paper, maybe you can find my paper on non-terrestrial networks. I work on this topic when I was with Ericsson and also work on this topic in 3GPP. So at this stage, I see the using AI ML for non-terrestrial networks. I can see interest come from the academic side and also some companies in the industry, but they have not show up from 3GPP side, because this is a brand new direction from the ecosystem perspective. So it's more important to focus on the basic functionality first to develop a common understanding before going to address verticals. Right? From non-terrestrial network perspective, satellite communication is relatively new compared to decades-long 3GPP. The work started around 2016, if I recall correctly. So I would say, if we want to see some, we expect there will be some work related to AI ML for non-terrestrial networks in the future, but not at this stage.
Okay, thanks. Yeah.
Hey, Xingqin, can you hear me?
Yes, I can hear you.
I have a quick question. It seems most machine learning research until now has used simulated data instead of real data in machine learning research for wireless. But recently, some really interesting real-world data sets have been appearing. And I'd like to know what's your opinion about these real-world data sets, and whether you think there's a place for them in machine learning research.
Yeah, I think data is certainly the foundation for all these data-driven AI ML algorithm. Right? From 3GPP perspective, in the current study, we stick to simulation data. That's because simulation methodology is well established within 3GPP community. All these major companies in the telecom industry, they have developed simulators, and they have been calibrated among 3GPP companies. So that's why from 3GPP study perspective, we stick to simulation data. But from real world deployment perspective, let's say if you want to use an AI ML model, it's likely, for example, site-specific data will be required. For example, if you want to train a positioning algorithm to do, if you get some input and then you want to predict your location, then all this will be likely site-specific, right? Then you have to use real data. So from I think real data is essential to real deployment of the AI ML algorithms.
Thank you. Just a quick follow-up. Do you think 3GPP might eventually participate in standardizing, say, datasets formats?
Dataset format, you mean, what do you mean by data format?
I mean, well, in simulation, the simulations vary tremendously, but when we are collecting real world data, since our objective is always to test in the real world and to make things work there, and perhaps to be interoperable between manufacturers, and the other question is whether you think 3GPP might standardize some dataset format or some data acquisition procedure for creating these datasets.
I think 3GPP will likely introduce some procedure or signaling to facilitate data collection. And this will likely be use case dependent, right? For example, if you look at the use case CSI feedback, that's totally different from positioning. So the data you need for CSI compression will be totally different from the data you utilize for positioning. But some common framework and signaling procedure will be defined by 3GPP, in my opinion. But the data set itself may not be standardized.
All right, any other questions? We are almost close to our usual time of closing. We have a few more minutes left. If you have any more questions, please unmute and ask. We would like to, thank Dr. Xingqin Lin for an excellent presentation and addressing all the questions and staying late to address all the questions. Thank you so much.
Thank you. Have a great evening.
Thank you. Bye, folks.
Bye-bye.